Good morning, all. Today I'll be talking about my thesis on high-performance silicon carbide modulators. Firstly, I'm going to give an introduction to the field which my research relates to. I'll go through the preliminary physics necessary to understand what I worked on. I'll then explain the two projects I completed during my thesis, namely on optimizing a broadband modulator and also on designing a new narrowband ultra-efficient electro-optic modulator. Finally, I'll present some future directions for my research. The modern world is becoming increasingly reliant on high-speed, reliable communication links which make up the backbone of telecommunication networks, data centers, and more. One promising technology emerging from the union of photonics with CMOS electronics is photonic integrated circuits, a photonic analog to electronic integrated circuits. At the heart of this convergence is the electro-optic modulator, which allows the encoding of electrical signals onto light. The ideal electro-optic modulator would be capable of direct integration with existing silicon electronics, allowing information to be seamlessly transferred between the electrical and optical domain on the same chip. If the integration process is compatible with CMOS fabrication facilities, then the existing facilities could be leveraged for rapid scalability. However, CMOS compatibility constrains the materials used and the fabrication processes involved. Silicon carbide is an emerging material in photonics research. It is a CMOS-compatible material, exhibits the linear electro-optic effect, and has exceptional electrical, mechanical, and radiation durability. These characteristics, along with the material's low optical loss, wide optical transparency window, and high breakdown voltage, indicate great potential for silicon carbide in CMOS electro-optics. Early this year, a team led by Professor Xiaoke developed the world's first silicon carbide electro-optic modulator, using a ring resonator design. A number of fabrication difficulties which have prevented the material's use until now were solved by the team at the Harvard Center for Nanoscale Systems. The work presented in my thesis relates to the optimization of a broadband modulator and also a resonant electrode structure to increase electro-optic efficiencies for narrowband operation using this new silicon carbide platform. Before I explain my work, I need to firstly present some preliminary physics. The linear electro-optic effect, or Pockels effect, is a change in the refractive index of a material linearly proportional to the applied electric field strength. In this formula, R represents the Pockels coefficient, which is dependent on the direction of the applied electric field through the crystal. One key performance metric of electro-optic modulators is the half-wave voltage, or V pi. It is defined as a voltage that must be applied to the modulator to induce a phase change of pi on the light. Similarly, it can be considered as the difference in voltages between full optical transmission and zero optical transmission. This diagram shows an example Mach-Zehnder interferometer structure, whereby total constructive interference occurs when no voltage is applied in A, and total destructive interference occurs when V pi is applied in B. Ring resonators are waveguides which loop back on themselves, forming a ring which exhibits resonance for input light for which the ring's optical path length is an integer multiple of the wavelength. Ring resonators allow exceptional wavelength selectivity with small footprints. Light is coupled into the ring evanescently from a nearby waveguide, and light of resonant wavelengths is coupled almost entirely out of the waveguide and dissipated in the ring. The formula for optical transmission is given here, and an example transmission spectrum is shown below, with its distinctive resonant notches. Electro-optic modulation can be achieved with ring resonators through changing the ring's refractive index to adjust the resonant wavelengths. By inputting light at a wavelength which is either resonant or near resonance, the refractive index can be modulated through an electric field caused by an applied voltage. Thereby, the amplitude of the passed light is modulated by the electrical signal. For my research, I optimized the cross-sectional geometry of the electro-optic modulator fabricated earlier this year. Geometric measurements were taken using focused ion beam analysis shown above. I modeled this cross-section using COMSOL multiphysics shown below, and analyzed its performance using the finite element method. Modal analysis allowed the group velocities and losses of the optical carrier, as well as the modulating RF waves to be computed. Here on the left is the simulated modal confinement of the optical mode in the silicon carbide waveguide, and on the right is the electric potential from a 1 GHz modulating signal applied to the electrodes. The normalized electro-optic overlap integral, whose formula is shown below, can be numerically computed in COMSOL, which expresses the degree of overlap of the optical and electric fields. The electro-optic efficiency of the modulator can be increased by decreasing the optical loss and increasing the overlap integral. These two performance metrics were used to optimize the geometry by adjusting the electrode thickness, electrode separation, silicon dioxide thickness, and the electrode waveguide offset. I compared the optimized cross-sectional design with two chip designs which had already been fabricated, which I will refer to as chip A and chip B. The optimized design showed a 7.09% increase in the electro-optic overlap over chip A and a 12.2% increase over chip B with similar optical losses. I'll now talk about the narrowband ultra-efficient modulator platform I designed. Microwave resonators near resonance can be modeled as series RLC circuits. From circuit theory, the quality factor, or Q factor, represents how much energy is stored in the resonator compared with how much energy is lost. In a series RLC circuit, the magnitude of the voltage across the capacitive element at resonance is equal to the magnitude of the applied voltage multiplied by the Q factor. So, if we want to increase the electric field through the waveguide, we can increase the voltage through resonant electrode designs. However, it is important to note that higher Q factors mean a slower decay of the power of the mode in the resonator, which limits the modulation bandwidth. This theory has been used in practical cryogenic microwave to optical transduction, as shown in the bottom right, which uses a quasi-lumped LC resonator for the electrodes. Sadly, this type of resonator doesn't work at room temperature because the increased conduction losses cause a decrease in the electric field across the ring's electrodes compared to a direct feed. I came up with a loop resonator design for the electrodes, which I have an example shown here. The ring's electrodes are located at the bottom of the loop. I used Sonnet software, which employs the method of moments to compute full-wave electromagnetic simulations of the design. The resonant circuit can be analyzed as a rectangular loop antenna, which is fed by a coplanar strip line. The resonant frequency occurs when the loop is equal to a lambda on 2 long transmission line, so we can match any arbitrary frequency by computing the effective dielectric permittivity and using these formulas here. To further improve the electric field and reduce return loss, I used quarter wave impedance matching techniques to match the input impedance of the loop resonator to a standard 50 ohms. Since the resonator's input impedance is purely real at resonance and is already inherently narrowband, the narrowband operation of the quarter wave matching section is suitable. Here's a comparison of the electric field strength at the ring's electrodes. That flat blue line down the bottom is the original design's simple capacitive electrodes. The 4 slightly higher field strengths are from non-impedance matched loop resonator designs. And that big light blue peak is from an impedance matched resonant electrode design. Quantitatively, the non-impedance matched resonator design shows a 302% increase in the electro-optic efficiency, and the impedance matched resonator design shows a 462% increase. Going forwards, we're going to fabricate my resonant design at the Research and Prototype Foundry here in Sydney. We have also already submitted an ROI to patent the design, and hopefully in the future we can publish a design using the resonantly enhanced electrodes. One really cool direction is to use the electrodes on phase shifters for optical beam forming. This can allow for energy efficient LiDAR. Also this summer, we're going to move towards a Mach-Zehnder interferometer modulator, which can have a larger modulation bandwidth. However, I found that the silicon carbide platform has a large optical and RF wave velocity mismatch, which degrades the modulation bandwidth. So we need to work on slow wave electrode designs. Finally, I was also a co-author of an application to ANSTO for radiation tolerance testing, which was accepted in June, but lockdown prevented us from carrying it out. Hopefully, this testing can be carried out early next year. Thank you for listening.